Hey, let's get started. This is about where we left off on Tuesday. Is the volume sound a little high to you? Loud. Let me drop it one notch here. Okay, should be good. I don't want to have too much echo, or else I'm going to just distract myself. So, function calls important. Frame pointer, stack pointer, pointers into your arguments. Again, spilling and filling. Right. Oops. Focus back. And you can certainly allocate additional things that are non-constant here as well, but they're all compiler directed. So the important point here is that in a language like C, you don't manage your own stack. That's all managed for you. And actually, if you sort of look at this notion of automatically allocated and reclaimed memory, if you're interested in things like the Rust model, you have to start here before you go into more interesting notions of how you can understand lifetimes of variables, and you can get the compiler to do that for you. Okay, let's free the top of your screen here. Okay. So, who knows what goes up here in the default MIPS ABI? You'll note that you're sort of missing a good chunk of memory here at the top of your address space. What goes up there? So remember how the other day I said that there's a bunch of code that you didn't write? Here's some code you didn't write. The operating system is going to live up here by default. Various portions of the operating system are going to map themselves into your address space. So the trick with our nice simple abstraction of, here's a flat, continuous, byte addressable memory space, 32-bit machine, there are 4 gigs of it, 64-bit machine, there's a whole lot more. It's a little more complicated in reality. In reality, that virtualization will actually allow things like sharing. The same physical memory can actually be mapped into multiple different spaces. This is useful not just for communication, but also, reuse of dynamic link libraries, all these other sorts of things. But a common model, and it's been modified in the past few years a little bit, is to reserve certain portions of that space for known portions of the operating system interfaces. Note that you will not have the same access you had to all of this. In fact, even across all of these different portions here, you don't have the same access. Your text segment, which is not text, it's your compiled binary, it's still called text. Don't ask, the names are old. Is read-only, right? So if you attempt to write into your text segment, you will get a seg fault, right? If you attempt to, access things that have not yet been allocated, you will get a seg fault, right? There are lots of protection bits set around here. In any relatively recent setup, this is not executable, right? So you can differentiate what is executable, or instructions to possibly what is writable. Some things are read-only, some things are write-only, right? Write-only is actually useful for buffers that are outgoing, right? I don't want to be able to, look at the internal state of whatever's being managed by some other piece. In practice, it's actually going to be even a little more funky than this. So the thing that we're not going to talk about too much now, but just do think about it. You'll note that when we learned how the ISA interacts with data, it really only knows how to talk about local data, i.e. registers, some implicit data, the PC, and this memory address space. So how do you do your I/O? Well, you map certain physical in and out ports to your I/O into the memory space and pretend that you're loading and storing to them. You memory mapped I/O, or you do some I/O control instructions. So certain portions of this are actually also going to be mapped for I/O, right? So they're actually going to be sort of virtual devices that are living there, where you don't actually have memory semantics, right? So for instance, I have a port and I read from it, and then I read from it again. I have no expectation that it has the same value. It's not memory, right? It's just a memory-shaped interface to something that is not memory at all. Lots of other stuff is fun in there. Okay. And as I said, there have been some changes here. So Spectre, Meltdown, allowing too much access, even with these permissions checks that are there, can be problematic because, as we will see in more depth later, the more complex your internals, the more the difference between the contract of one instruction to completion at a time, followed by the next one, versus how you actually did it, i.e. a few hundred instructions in parallel, speculatively, right? And then you just fix it at the end. The more that those diverge, the more that you can find breadcrumbs of things that never technically happened, right? And so even if you don't actually have permission to access some of this data, you can generate some wrong path code, which leaves some breadcrumbs around of what might have actually been there, and then reconstruct some data from there. So there's all sorts of fun security things that actually come from inter-process mapping, but it's still something to keep in the back of your head. Okay, now something that, well, this is still a set of review slides. This is going to be new to most of you, right? Atomic exchange instructions. Okay, so again, even before, right? So even before we had to worry about, chip multiprocessors, even when we're still in our uniprocessor space, we still needed to worry about synchronization, right? So again, that memory model, if your instructions are load and store, and you have multiple threads, or even if you have one processor and the threads are interleaving in sequence, old mainframe style, then if you load something and then you go back and you want to act on that data, you can't actually know that nothing has changed it between when you accessed it and when something else accessed it, right? So your von Neumann ISA interface, that model is very simple, but in the case of multiprocessors, it's a little too simple, right? So the sequencing is entirely local. One instruction to its completion at a time, one after the other, but it doesn't tell you anything about what any other sequencer is doing. So your ISA has contracts and understandings of the fact that there may be arbitrary interleaving of instructions from any other sequencer, and your code still has to work. And when I say sequencer, usually we're talking about threads, but threads versus processes versus other mechanisms doesn't really matter here, right? Something that is sequencing your instructions. So if you want your ISA to actually be useful for anything other than a dedicated embedded machine, you're going to need to have some sort of instructions that allow you to perform synchronizations. Or, and if you want to have an extremely conservative consistency model, it turns out there are algorithmic approaches to do this with just loads and stores. These techniques were discovered in the 1970s, but trust me, you want hardware support for this. You don't want some large data structure that you have to wander through and an incredibly restrictive consistency model just to be able to get two things to agree on which one happened first, when I can do that much simpler with a little bit of hardware sprinkling dust, right? Okay, so we will be focusing more on this towards the end when we actually hit the multiprocessor space. These are out there as well. Depending on which ISA you're interested in, there's some different design choices that have been made. So there's some very old style, like test and set, they're still sitting there in an x86, but hopefully nothing you generate will ever use those again, right? So legacy code only. The model for modern x86 machines is the compare and swap instruction, right? And so you'll notice for all these atomic primitives, they have a pattern that you could call read, modify, write, right? So a load only loads, a store only stores. Atomic instructions tend to both read and modify a value atomically, right? Uninterruptibly. Right? So compare and swap is going to look at some value in memory and then conditionally swap it with some other value based on this comparison. If you're looking at MIPS, you're going to be looking at something that's actually a pair of instructions, load locked, also known as load linked, LL, and a store conditional, right? So I'm going to perform a load on some particular operation. I'm going to set some metadata and condition on that metadata still being valid. We'll look at that when we look at cache coherence. then my store to that same location will succeed. Otherwise, it will fail. Right? They have different drawbacks. LLSC has some nice implementations along with caches, but it can result in live lock. CAS is a little cleaner. There's also an entire family of these that have been explored that you can call fetch and fee. Right? So fetch and fee, or some fee function. So fetch and increment, fetch and subtract, fetch and fetch and or. Right? So you load a value, you're going to get whatever the current value was, and you're going to apply some operation to it as well. Right? So you can imagine if you're implementing a barrier, fetch and increment's pretty useful. Get me the current number of things that were sitting there on the semaphore and increment it by 1. I can do that in one instruction atomically, very nice. The reason that those have been explored pretty heavily is that they compose. So if I have 2 fetch and increments, I can add 2. Or you can actually figure out that to do that in network or at the memory controller. So anyway, we'll come back to these more. These are new, so I spent a little more time on them, even though it's we're not going to go into any depth here. But be aware that there are some special flavors of memory access that are going to come. All right, so here's the MIPS version, load linked and store conditional. Okay, so load linked looks a lot like a load. Semantics are almost the same as a load, except there's going to be some additional metadata that's stored. And then store conditional will only succeed if these additional bits that have been set here have not been unset. Right? How that's going to give you something atomic, we'll go over later. But if any of you have played around with transactions, think of this as the world's smallest transaction. And you're not too far off. It's a cache line sized transaction. Okay. So when you look at what various programs, as we go, we've mentioned multiple times that depending on your workload, you're going to design your machine very differently. Here's one of the reasons why. Right. So if you look at FP versus int, the density of computation numerically is radically different. Unsurprisingly, floating point applications that spend most of the time doing linear algebra spend most of the time doing arithmetic. And branchy programs that are doing lots and lots and lots of decisions spend a lot more time branching and less time actually computing. Right? So if you're trying to narrow down which of the 27 cases you're in, right, your code is going to look very different than if you are just, for the entirety of this vector, add 1. The entirety of this next vector, multiply it by this other vector over and over and over again. In both cases, data transfer, your loads and stores, and these are in fact dominated by loads. Loads are much more common than stores, are one of the largest classes of instruction. Excuse me. In any load store machine, these are going to be fairly frequent. Right? You don't have enough registers. So unless your data is so small, it's register resident. Right? So unless you're dealing with something that literally has only 30 variables and you're going to do lots and lots of computation on these 30 variables, I'm sure someone could write a very clever tic-tac-toe algorithm that does that, but you're going to be moving things in and out of memory. And again, think of this from a technological trend perspective, right? This is going to be one of your pain points that does not get better very much as technology improves. Certainly the relative cost of this and this continue to diverge, right? Branches, jumps are rare. We don't even bother to talk about the different types of jumps because they're all down here in the single digits. Anyone who's ever, how many people have ever heard of control flow integrity analysis from a security perspective? No? Okay. So control flow integrity analysis basically is practical because these are statically analyzable and your jump registers aren't, but they're rare. So you can throw some additional code overhead on it to actually analyze them dynamically, and the rest of it you can get over statically. Okay. Logical operations, they are around as well. Shifts and ands and masks and so forth. They're cheap. You could even sort of fold those into the arithmetic portion, and it wouldn't be too far off. They're just cheaper versions of arithmetic, is the right way of looking at that. So you just have two classes of arithmetic there. So the ones that are going to cause you the most pain, these and these. Not so much in this workload, right? So that's why you get differently designed machines. Okay. So, the RISC-CIS debate has mostly long since ended, but we'll keep reminding you how it actually played out. So one way of looking at it is that x86 won, even though it was CISC, it wasn't a very good design paradigm because of the economic impact of binary compatibility. But binary compatibility doesn't mean that our ISA doesn't change. It means it's append only, right? The number of instructions in x86 keeps getting bigger. And in fact, even if you look at modern, sort of one of the more modern, most modern even RISC ISAs, RISC-V, RISC-V is explicitly extensible, right? It's actually got a bunch of codes in it that allow you to extend the instruction set for various additional purposes. You can even extend the size of instructions with some various modes in there. So the idea is you're going to keep adding more instructions, right? That's just sort of inevitable. We find new things we think are important enough to actually have hardware do directly, right? Interfaces need to be backwards compatible, or else you lose all of your software environment, right? But you do actually come up with new things. Now, the other thing here, anyone want to guess what the majority of these new instructions are actually doing? Reasons you can support this model without sort of radically worrying about these very, very different binaries? No, it's a particular paradigm. And it's one where actually it's intentionally supplanting previous sets of instructions that it just added not too many years before. Mostly no. I mean, occasionally you get some new things. So you do occasionally get new architectural features. So around 2012, I want to say, is when transactional memory extensions came in. So you get some fundamentally new stuff sometimes. Virtualization came in, transactional memory came in. This is actually a very old paradigm, but they keep adding more and more of these instructions. I'll give you a hint, they keep getting bigger. Yeah, one of the biggest sources of growth are the SIMD extensions, SSE, AVX, and of course they keep coming with new ones, AVX 256, AVX 512, right? So it's easy to lie with numbers, right? These are true numbers, but the right way to interpret how many of these new instructions were novel and how many of these new instructions were just wider versions of old instructions in the SIMD space, do keep that in mind. So in particular, yeah, the jumps to all through all the SSEs, and if you were to extend this further, the AVX versions are dominating a lot of that. So they do append only, they do grow, but they grow often by just having you not use the older versions. Okay, so if you want to sort of look at the whole setup here, there's your machine code, right? That used to be assembly language, that used to be some higher level program probably, right? So these are sort of all of the pieces on the path, but again, always keep in the back of your mind that even if this is all that you wrote, there is more code, right? So your C compiler will take this into this as part of an intermediate step. These days, if you're looking at something like this would be sort of the role of Clang to get this into not directly into the final MIPS assembly, but into an LVMIR, and then the LVMIR going into the target backend. There are about 7 levels of lowering, right? So it has a whole bunch of internal passes where it takes an internal representation and gets it closer and closer and closer to the particular semantics of a backend, does some final optimizations on it, and then finally emits a binary. This last part here is pretty trivial. This is all one-to-one. Okay. Keeping in mind, again, your optimization level is existing, already tells you this is a one-to-many optimization, right? So there are very, very many different ways that I could produce code that does this, right? So from O0 to O3, right? So for instance, if I do compile with O0, I'm not allowed to actually promote variables to registers. And so everything that lives on my stack gets memory accesses, whether or not it really needs it or not, right? It's a sort of a, very rote representation of exactly everything that was in the original program. As you go to O1, it starts doing register promotion. You go up to O2 and O3, you get your dead code elimination, your loop unrolling, all these other sorts of things. You can get lots and lots of different versions. This part, one-to-one, right? So not very interesting. Okay. Now here's sort of the rest of the stuff that's actually happening, right? So you have some object code that is not yet your program, right? So every one of your source files is going to turn into some piece of object code, right? All the code that's actually in that particular, coming from that particular set of source. And then you have a linker, right? So your linker is going to take multiple different object files, some of which you wrote, some of which other people wrote, some of which are shared libraries, some of which are statically linkable libraries. And it's actually going to do some binary rewriting, right? That's kind of the linker's job. Linkers actually, you can think of as very loosely being cross-modifying code, right? They actually go in and take all the labels in here, which were external references, they resolve them, right? They move things around, right? For instance, if you have a bunch of objects, you don't actually know what the relative object order is going to be in that text segment. I don't actually know what my actual address of anything is going to be until I start linking, right? So that's where you also get to phrases like position independent, these sorts of things. Okay, so now you have executable. This is still not a program, right? This is the statically compiled binary version of all of the code that is specific to this program. But it's not really a program until you actually try to load it into memory. There's one more step. There's a loader that is going to go through and actually do one more pass. If any of these things were dynamically linked libraries rather than statically linked libraries, it still has to go and find them, make sure that they're in memory, and now actually do some in-memory binary rewriting for those last remaining labels, or otherwise set up your trampolines so that you can basically have the code to dynamically do the binary rewriting as it tries to load them lazily, right? The various optimizations you do there. And one of the things in particular that's likely need to be pulled in, some system runtimes. And then finally, when that's in memory and there's a sequencer attached, great. Now you finally have a program, right? Okay. So what does all this get you versus, say, your normal model, starting in day one of CS of, well, I just opened Python and started typing stuff. Why do I worry about all these more complicated things? So I'll give you a short version. Even in Python, how many people have ever heard of Cython or PyPy or any of the successor projects? So Python can be compiled, right? You can compile Python, right? The default interpreter doesn't. It runs entirely in interpreter mode, but you can, and you will get almost certainly about a 4 to 5x improvement on your performance from doing that, unless your Python code was 2 lines calling SciPy in the first place, which is already precompiled. Because it turns out you can call things across languages as well. Anyway, so here's some experiments from they're from yesteryear. Don't look too much at the versions. But the trend here is still remains very much the same. So if you do an O0, turn off optimizations, don't optimize anything, and you normalize relative to that, so that's your 1, right? Then you get some interesting things here. So again, the end of the day, what we really care about is the amount of time it took. So these are all in the same machine, so you can interpret time from this column alone. Right, so good news, turning on the largest level optimizations was faster. Marginal returns though, right, you get your biggest bang from the buck from trying anything at all. Right, the rest of it you have to go a little deeper to get much. Now the CPI, interestingly enough, is the lowest for the unoptimized code. You have an idea why that might be? Why might your completely unoptimized code have a very low CPI? So low CPI is generally good, right? Well, if you look at the number of instructions, it's doing a lot of simple, stupid work, right? So if it's spending a lot of its time just basically taking, every time you do I++, right? If I++ is load I, increment I, store I back, right? It's going to be a cache hit, right? It's just doing a lot of useless but very simple work, right? So that's why the CPI alone is misleading. instruction count alone doesn't necessarily tell you everything either, because again, this is the fastest, executes more instructions. We're just sort of confirming that the execution time equation is what you actually want, right? So all these factors play out. One of the reasons you can get, so this is the dynamic instruction account. You do often actually, in particular, get, unless you have specifically set the flags, you can get some larger binaries coming out of here. It turns out a number of the trade-offs you can make in the compiler are to increase the total number of instructions statically, right? With things like loop unrolling, allow much better scheduling options. But there you go. Okay. So there you go. Yeah, so it's kind of interesting. Now, if you're looking for something that is somewhere in between C and your, Python, why would I ever compile anything? You can look at something like Java. So here's how the Java setup would work. Take your Java program. It does compile it, but doesn't compile it into native target code. It compiles it into Java bytecode, which, as we did mention, is a stack machine for reasons. And then this can be just interpreted on the Java virtual machine. So every one of the Java bytecodes is basically going to dispatch to some precompiled function with all of the pieces of it being arguments, right? And some of these have been reasonably heavily optimized, and some of them, well, some of them less so. And then what Java will do is it will dynamically figure out whether or not some of your sequences of code are frequently executed, and actually compile them all the way down to host machine, and then do dynamic binary rewriting so that every time that you actually try to re-execute that same path, it goes and executes the native code instead. So if you sort of then look at how that plays out, and again, if you want to sort of understand how something like PyPy versus your default Python is going to work, these sorts of numbers here are probably the right way to look at things. You do get a lot of speed up from actually compiling things. Okay. So again, here, this is a slightly different experiment, bubble sort, quick sort, with without optimizations, Java versus C. So, your C code is still going to be a bit faster. So this is all normalized to your default C code here, right? But the gap closes quite a bit once you've actually aggressively compiled it, right? So the takeaway should be, at least when you get finally down to the architecture level, assuming that your compiler can target your architecture well, the base language shouldn't be too much of a problem by the end, but not actually targeting the base architecture at all, right, is still a bit of a problem. Right, so emulating other people's designs, like emulating a stack machine on your machine is not a great idea, but anything else is probably fine. Okay, we're going to go through this next section here quite quickly, and I want to leave enough time at the end to try out Kahoot. This is not something we're going to go into in a whole lot of depth. This is, again, mostly to make sure that you have the right intuitions about the relative cost or difficulty of different components. Okay, so the vast majority of instructions which are going to do arithmetic of some flavor are going to just be down in the 32-bit ALU. Not all of them are, right? So your multiplies, your divides, they're going to get their own unit. Your branches, you eventually push, to simpler comparisons, further up the pipeline. But all your adds, all your subs, all these other sorts of things live in, your arithmetic logic unit, your standard 32-bit style ALU. And they're relatively cheap and they're relatively fast. Right, so if you think about the simplest adder you could build, a ripple carry adder, right? It's linear in the number of bits. You can count the number of gates in a full adder cell. So if you wanted to, figure out exactly how many, transistors there were in a very, very naive ripple carry adder, would be pretty simple. We don't build ripple carry adders because they're too slow. You do something like a Koge Stone or something, some logarithmic speed adder. But adders are very fast. They're very small, and you can build a lot of them. The Boolean operations are even faster and even smaller, since they're all just in parallel. There's no carry chain. Okay. There are lots of things that you do actually have to think about at least a little bit. This is maybe something a little more to think about in terms of design for ISA. how do you want to handle your immediates, and how do you want to handle when something goes weird, right? What should happen when divide by zero happens? Whose job is it to notice this happened? This is a design decision. You could just say it's software's job to have not told me to divide by zero, and I'm free to return whatever the heck I want when you ask for divide by zero. Or I can say it's hardware's job to figure out that you had to divide by zero, and then software's job to handle the exception that comes up and not crash, right? So design decision. Okay. Beyond that, in somewhat more modern machines than the one we looked at in C331, you are going to have operations for multimedia or other forms of data parallel computation. All right. So one of the first things that people did was subword parallelism. Why? Again, it's not how you build it, but it's a sufficient mental model. Think back to your ripple carry adder. What happened if I just cut the carry chain in a few places, right? If I have a 32-bit adder and I cut it every 8 bits, I have 8 adders. I have four 8-bit adders. So this is actually a very cheap way to overlay computation on top of your additional hardware. So the right way to think about this is a very low additional cost in hardware, right? I don't have to modify my adders very much. I just put a conditional mux in there as to carry in with a 0 or whatever we had before, right, from the actual carry chain. And now I have the ability to operate on multiple smaller pieces of data in parallel, right? So the nice thing with the single instruction multiple data paradigm is the single instruction part, right? The multiple data is nice, but from thinking about it, this is still very much a von Neumann model. I have one instruction. I'm applying one operation. I'm just applying it to a bunch of pieces of data, right? If I'm doing the subword, then I don't even really have to change any of my memory semantics. Everything else is still going to flow exactly the same way. This is a very nice, simple, excuse me, low-cost, high-reward modification, right? Now, as you go up to things that are definitely not subword, like say AVX 512, because it's 512 bits wide, clearly you had to make a bunch of other modifications and compromises. It's not cheap, right? In particular, as you go to things like AVX 512, those actually start to look like vector machine models where they actually have to have a notion of vector registers, of masking, of all sorts of complicated things. But the first things that we got, MMX on the Intel side, for instance, really were focused mostly on subword quantities, which was fine because 8 bits is one of your fields in a pixel, and you can do a bunch of stuff nicely that way. We'll, by the end of this class, look at some alternative models to SIMD for handling data parallelism, namely SIMT. When we look at GPUs, they're similar, but importantly different. Okay. Yep. So just chop it up. Okay. Multipliers are large. I don't need you to remember exactly how to do, Boolean multiplication. I don't need you to understand Booth encoding. Right? I don't need to understand Wallace trees. What I need to understand is multipliers are large. And if you don't want your multiplier to be large, it's going to be very slow. This is your choice, right? Because I can build a multiplication out of shifting and adding. So if I have a shifter and an adder, I have a multiplier eventually, right? But it's going to take a lot of time. If I want to do it all at once, it's very big, right? It's effectively an n squared as a function of the number of bits. If you're doing it naively with an array multiplier, you're going to do better than that with something like a Wallace tree, but it's large. Right? So what this means in practice, if you want sort of a good rule of thumb, if you think about how many multipliers, integer multipliers, could I fit in the same area that I would put, say, the processor coming out of your final project in 331, a very simple integer data path with some little caching support, maybe 10 multipliers per, right? So a multiplier is like 1/10 the size of a small in-order core. Right. So these are big and expensive. You need at least the ability to do multiplication in practice, but it's expensive enough that certainly in deeply embedded devices, if you don't need it to be fast, sometimes you just didn't spend the money. At modern scales, again, well, I say it's expensive. It's only expensive relative to the other pieces, right? I mean, compared to cache, this is still pretty cheap. But compared to an adder, it's very, very big. Compared to a register, it's very, very big. The other thing to start thinking about, and this we're not going to come back to for quite a while, while the area costs of these are a static decision, there's some other costs that are more dynamic, right? So it will turn out that multiplying by 0, which happens, doesn't actually cost as much energy as multiplying, two random numbers. So you will actually have data-dependent properties dynamically. And if you have ever looked at the various optimizations for handling sparsity in linear algebra, or for dealing with the fairly large number of zeros produced in a ReLU-based neural network, there are all sorts of optimizations that are basically trying to save time and or energy, understanding that the zero is a different case. But when this goes back to actually measuring things, this can actually be fairly important, and you can get a range, right? So if I want to understand how much energy on average my multiplier burns, I actually do need to understand what on average my inputs are, right? It's actually bit pattern dependent. If I want to understand how long it takes, now it's the same, right? Because I do worst case. Right? I look at my worst case pattern, I figure out how long it takes. My area cost is fixed at design time, but power is much more dynamic. This is actually one of the reasons why it took a lot longer to get good power models. Right? So if I want to understand how many cycles something took when I'm doing a design space exploration, figure out how I should build my processor, right? I don't need to worry about input dependence. Right? If I want to understand whether I have a power optimal design down at the standard cell level, I need to figure out which wire is more likely carrying, a signal longer distances that's actually going to fire. Glitching, all sorts of other fun stuff. So power just turns out to be a little hard to measure. Again, because multipliers are large and they're slow, they get handled a little bit differently. So you have the high and the low registers. Also, it has to do with the amount of precision, right? So I'm not going to dwell on this, right? Obviously, I need 64 bits to have a 64-bit output. Okay. Division is so it has good news and bad news. So if I don't care about being fast, right, because division does not parallelize very well, right, I got a bunch of conditional checks, right? I'm going to basically go through this process sequentially. Then you tend to use a fairly hardware cheap approach for it, certainly for integer division. Integer division also turns out to be stupefyingly rare, right? I don't do a lot of integer division in most code, right? Or at least you find ways to do your integer division using something other than actually division, right? So in particular, say you're doing modulo. If your modulo is a power of 2, congratulations, you don't need to actually do integer division. You can use logical operators, right? These sorts of things. Or if you're dividing by a constant, there are ways you can refactor that, right, into other forms. It's slow. Now you can have big and fast division. You can get it's a little complicated. Anyone who's interested in how you make a floating point divider faster, they're still slow, relatively speaking. But if you want to actually generate multiple bits per cycle, a good place to start is something called SRT division. It uses a redundant numerical encoding. So you can actually have both positive and negative digits, and it uses a convergence algorithm with a lookup table for bounding, right? How far off you could be and still converge, looking only at a subset of the digits at a time. So you look at 4 bits at a time, right? And you look into a table, and it says, okay, well, we don't know what the actual final answer is, but looking at these bits, I can bound it, and it's safe for this to be your answer. You'll be able to converge looking at the rest of the bits later since you can both add and subtract from whatever your current value is. This is also where the billion-dollar FOOF bug came from. The Intel Pentium division error was a entry that was wrong in that lookup table. All right, so that's worth mentioning just to understand how things go wrong. Okay, the divide again uses special registers and MIPS. We're not going to dwell too much on it because it's, well, really, really rare. Okay. Okay, floating point numbers, very important. Right, so again, the key thing you want to think about with floating point versus fixed point, if you have something that is non-integer, but the range is very well defined, right, then you can use fixed point approaches. They're reasonably nice narrow range, right? Or I can just renormalize what my unit of measure is until it's my smallest one thing, and then back to integer land. But if I want to simultaneously talk about the age of the Earth and one atomic mass unit in the same computation, yeah, you want floating point. You want something that covers a very, very large range of values with one representation and has a bunch of well-defined math rules on how they interact. Right. So another way of thinking about that, say you want to talk about gravitational attraction, right? The mass of the Earth is very large, the gravitational constant is very small, right? You don't want to have to worry about whether you ran out of bits in your fixed point representation, partway through some intermediate result in a series of multiplications and the Euclidean distance formula and to figure out what the actual gravitational attraction between two objects in a solar system are. Right? Okay. So this has been around actually about as long as MIPS. So the IEEE 754 standard also came out in around 86. It's had some modifications since. So sign, exponent, fractional bits. Right. So our base here is 2. Our exponent is biased. Again, we're not going to quiz you on the specifics of the representation, but just to sort of know how these things are operating. So again, if you think about the hardware costs, right, this is the part that ultimately is going to be doing some of the multiplying and adding separate from this. So you're going to get a couple of different multiplier adder paths here, neither of which is a full 32 bits wide. But there are more of them to compute some of these operations, and there's a lot of shifting to get it to get multiple floating points into a common representation they can actually look at. Now, precision and accuracy are different things. Okay, so if you look at the relative accuracy of floating point numbers, they are compared to what they're trying to represent, that is relatively uniform across the entire value space. That's by design. Right. So if you look at as a percentage of the value that you were trying to actually represent, how close is the closest floating point number? That bound is very nice, because what happens is every time my range doubles, I lose 1 bit. Right. So I have a range that's twice as big. So my number is twice as big, and I have 1 less bit to represent. That means actually I had exactly the same accuracy as I did over the previous range. You think about the other way. The smaller the quantity, the more bits I had to represent it. Okay. Precision, however, right, if you care about a particular size, like let's say that you care about millimeters at solar system scale, right, then you have different challenges. Right, if you just want relative accuracy, this is fine. If you want particular precision, right, this is a different quantity. We're not going to cover this in this class, but it has some interesting interactions with the way that these hardwares have been built historically. And if you want to sort of flip through that, okay, then it's the classes they're relevant are 451, 455, and 456, I believe. Right, so numerical analysis. When you are actually dealing with large, complex scientific computations, you do actually need to sort of understand where and when you're losing bits. The only thing you really want to bake into here that I need you to remember, remember that floating point math is neither associative nor commutative. Right? These are not the reals. These are IEEE 754. It's not associative. It is not commutative. And this will have implications when you think about what the compiler can do to reorder things. Right? So if reordering things changes your equation, right, or factoring things out changes your equation, the compiler won't do it. Right? Compilers are conservative. Right? Similarly, the hardware that is going to be operating on these, when it starts making its own dynamic scheduling decisions, is going to have some of the same constraints further down the line. Okay. Okay, so we got floating, we get double. Double's just bigger, more bits, more precision. Normalized storm magnitude means that there is a hidden 1. Yes, there's the d-norm space. We're going to pretend it doesn't exist. Just pretend its name is Bruno and move on. The bias helps you sort things, so you can use the same comparators you built before, which is clever, but again doesn't really matter too much. Some other things that are actually important out there. Floating point is also able to handle infinities, right? So anything you think about a useful mathematical concept, someone probably thought about it. Again, we're not going to talk about the d-norms. If you get not a number, so if you divide by 0, if you divide a non-zero value by 0, you get plus or minus infinity depending on the signs. If you divide 0 by 0, you will get not a number, right? So it does say, look, there's some things that this is ill-defined. True 0, you'll note that doesn't show the sign bit here. Yes, both positive and negative 0 do exist. Okay, so the floating point gets its own set of register own set of registers. There's a key reason for this, right? Your integer code and your floating point code are only loosely coupled, right? I don't do a bunch of integer math on floating point values and vice versa, right? So all of the operands that are going to feed into my floating point ALU are going to come from the floating point register file, and then they interact via basically load stores and movement instructions between the two register files, right? So anytime you start to think about cluster designs, I think you can break off a loosely coupled piece, you can play the same trick, right? I don't want to have a register file that is twice as big that I mostly don't use. That's a bad investment. But I can have a separate register file because there's some nonlinear scaling in there, right? It's cheaper to build 2 register files, each of size k over 2, right, than 1 register file of size k. Right? So k over 2 squared plus k over 2 squared is less than k squared. Right? So this is going to show up a bunch of times in terms of how we scale some of these structures. Anytime you can partition them, even weakly, it's a great win on the hardware space. Okay. So we're not going to dwell too much on the particulars. How does it deal with doubles? It deals with doubles a little oddly. It spreads them across 2 single-sized registers. That's a MIPSism. Again, the only utility there is if you actually are going to read some floating point examples. Don't worry too much about it. You can tell whether or not you're working on floating point, single size or double size by the extension. Yes.
When we're looking at the cost of the FPALU, similar to
so again, it depends on your performance optimizations. So add in particular is quite a bit more expensive. So if you think about the process of doing an integer add, I present my 2 integers and then I add them. To a floating point add, I take my 2 floating point values, I align them into the same exponent space, which actually figures out, I have to figure out which of them has the larger and which of them has the smaller exponent. So I need to have a sort of potentially a swizzle between my A and my B operators. Operands, right? So that the right one is in the shift, the correct one is in the shifter. There has to be a shifter so that I can actually do that alignment that is based on the exponent, and then only then can I actually do the add, and then I have to put it back into floating point format and renormalize it at the end. So there are a larger series of steps, right? To restore the hidden bits, if with the exception of the d-norms that exist, get them into the same representation. Because with floating point, effectively, you have multiple possible representations. You actually have to understand what happened to the bits you may have lost during shifting. So floating point has a bunch of hardware support for rounding. So you have your rounding bits, your guard bits, right. So you can actually understand whether or not the value you have is slightly more than what you have, or everything you lost was 0. You can behave differently for rounding. You can understand how and when you're losing precision. And you can actually set multiple rounding modes. So if you want to talk about some of the complexity here, is that actually there are a lot of different things in the specification that it's supposed to support. They're not necessarily used that often, but they can be specified, and so it has to be configurable. So more muxes. Multiply is a little nicer, but you do still have to do the pieces separately, right? Because you can treat the exponent and just accordingly to figure out what the final exponent is and what these are more in parallel. But with this is very sequential. Divide, square root. So all of the other complex operations also get thrown in here too. So square root, cosine, all the trig, logs. There are a whole bunch of different ways that you can implement these. One of the standard ones is quartic. But you can do these fixed number of iteration iterative approximation algorithms that are table driven that will get you within the right number of bits pretty quickly. Different area costs versus time costs in terms of how you want to implement those. Yeah. So the floating point ALU with all of these other features is much larger at the very least, and in general more expensive in other ways as well. So this again was one of the reasons why in the initial MIPS this was treated as a coprocessor, because they weren't even sure they were going to have the real estate to put this on all their designs. Now obviously I can emulate all of the things that are done here in software, and a lot of machines did. So actually, if you look at what was happening on the x86 side, if you had the difference between a 3D6SX and a 3D6DX chip, the 3D6SX had no floating point unit. So anytime that you executed a floating point instruction on the 3D6SX, it basically triggered an exception, jumped over to some software emulation code and ran it all in software, and then jumped back, right? And a 3D6DX had an x87 floating point unit on it. Fun fact for the x87, it took a little while for full compliance with and interactions with IEEE 754, is it uses 80-bit representations internally for historical reasons. You know, again, if you really care about that, take an numerical analysis class, but for everyone else, we're still sort of stuck with that for old default x86 floating point code. Interestingly enough, because other than the multimedia space, a lot of things that we used data parallel instructions on turns out to be floating point data. A lot of the modern, the x87 also a stack machine, which I guess for doing math is actually very usable. Think calculator. A lot of the modern floating point code that you would run often does run using the current SIMD instructions. So if you can remap things onto SSE or AVX, you'll actually get in general better performance than and some cleaner interfaces than running old school x87 code. But yeah, these are big enough that you can actually, if you look at a die photo, you can get a sense of actually sort of trying to see this unit collectively. Again, some of these are tables, like for the divider square root, so that makes them larger. But you can't see an integer ALU unless you're looking at a very old design. It's very zoomed in. They're too small. But the FPUs you can still see. Okay. They still got stuff in and out of memory, but the arithmetic looks a little different. You do need to have some comparison operations, just because you don't want to be having to move things back and forth between the integer and floating point registers to do all of your branching. Certainly anything that is data dependent on a floating point in order to branch. But these are less common in practice. Again, you're going to have a very common comparison against 0, but comparing against 0, at least there in floating point, that's still pretty easy, right? They're 2 zeros, but you know, it's still not very difficult. But this type of condition just occurs less in the code, right? Because you're usually doing something that's data independent. If I multiply 2 matrices, I don't care what the data was, unless I'm trying to do a sparse matrix optimization, in which case I care about, was it 0, right? But you know, you do need that support there. You don't want to be moving things back and forth. Again, think in the back of your head, moving things is expensive, right? And keeps getting more and more expensive as the year ticks by. The relative cost of moving data versus computing on it, certainly from an energy perspective, right? Time is a little more complex, but from an energy perspective is quite bad, right? So by 2015, you're at the point where moving data, moving one operand, one 64-bit floating point operand, 1 millimeter, is about the same amount of energy as doing a floating point multiply accumulate using that operand. And it's gotten worse since then, right? So those are some good rules to think about in the back of your head. Yes?
What's the average distance?
It's a good question. So that depends a lot on your design and your workload. So it's a question of your data locality, right? But if you think about the scale of a modern chip. Now there's some different approaches now with chiplets versus monolithic designs. But a good sized die, something like this is a pretty good sized die, 20 by 30 millimeter. That is a fairly expensive design. I think for that Zen 3, you're looking the primary, not the IO chip, but the primary chiplets on the order of around 200 millimeters squared. Right. So these things they're pretty small. And you can do some back of the envelopes with the speed of light to see how far you could actually get in your 200 picosecond clock cycle. Remembering that you do need some initial driving time and setup time to actually both generate and receive a signal. So you have less than 200 picoseconds. And you can start to understand that if you're looking at something other than optics, and you start to look at the speed of signal transmission in copper, which is 50, 60% of that, you can see that this is actually quite large compared to the time that it takes today to move. But yeah, the energy stuff is no fun these days. So we'll get more on that later. But your goal is to have them move as little as possible, right? How much control you have over that is a little challenging. But if you look at, in fact, a modern machine with dynamic scheduling, with a virtualized register file with a few hundred registers, your register access is 3 or 4 cycles. Right? You're no longer even get a single register out, and that's mostly a function of size. Right? Just drive strength and distance and moving things along through the wires and lighting stuff up and take a few cycles. Your cache is going to be 3 or 4 cycles as well. Yeah. And those are only a few millimeters on a side. Yeah. Okay. So again, if you look at the sort of breakdown, right, we saw the overall breakdown here. This is just sort of driving it a little deeper. Right? When we talked about, we do some arithmetic. Well, what is the fraction of particular arithmetic instructions? Right? You can see that the adds are very common here. You can see that the multiplies should show up. Yeah, multiply is a lot more common here on floating point. Integer multiplication, not nearly as common, doesn't even make the 3% cutoff. Right? Division doesn't make the cutoff on either list. Right? Everyone tries to find ways to avoid division. Right. A lot of shifting and logical stuff is doing these sort of smaller constant bit manipulations. You can see the relative number of loads and stores here. This is a pretty good ratio, reasonably indicative, usually about twice as many loads as stores, give or take. And then you can see some different flavors, right? Load byte, things other than word-sized objects. Right? So you're doing string manipulation. And then these collectively here are all of your control-related operations. Whereas here, you can again see the control operations don't really make the cut, because if I want to have better efficiency, I just unroll more and more and more of my loop doing my linear algebra, right? I don't need a whole lot of branches to do for I equals 1 to 1,000,000, right? And optimize that mostly out. Okay, SpecInt does have some floating point values in it, but they're fairly rare in that particular benchmark set. But even if you have an integer heavy workload, you do still want some floating point support. Yeah, and similarly, even in a SpecFP workload, you can see there's a bunch of integer code here that does still get run. So a lot of the control code that is sort of wrapped around controlling, a lot of the code that is designed to do the operand fetch. Right, so my data is all floating point, but my addresses for my array are all integers. Right, so I'm still doing integer math to walk through the array and keep my floating point unit fed, but not vice versa. And again, you'll note that the biggest lines here don't line up. So your workload matters when designing your processor. I'll say it a few hundred more times. Okay, well, we'll sort of skip over this. It's not too important. Just remember that left shift and right shift are not opposite operators with respect to what their arithmetic equivalent is, right? So if I do a left shift, that is multiplication. If I do a right shift, that is not division. This is the one I do really want to have you keep in the back of your head, because it will actually affect how some of the optimizations that we want to perform can actually work out, right? So basically, I think that should be 455 and 456. I think there's an off by one error there. Okay, how much time do we have left? We'll go a little further. Okay, so let's remind ourselves of where we're sort of starting with your default data path, right? This is enough to implement all this ISA stuff we've seen. It's not what you want to build. It's in fact, as we already know, a pretty bad processor. Doesn't have pipelining yet, but this is enough, right? So again, the bar to being a processor is very, very low, right? So everything after this is how do we make it a good processor, right? And so if you think about why we first moved, right, from the most sort of brain dead, do this all in one cycle version of this loop, right, that just supports the union of all of the things necessary for all of the instructions that are supported, right? It's going to be because you have relatively low utilization of a lot of the hardware resources in that model, right? And in particular, different instruction classes make different use of different resources. Now, again, forward pointer here. If I have the simplest processor I'm building, I need at least one of everything. When I start scaling up, if I scale up and I want to do, rather than one instruction at a time, I want to do 4 instructions at a time, that doesn't mean I need 4 of everything, right? So again, think back to those distributions of different instruction classes. If I only expect, 20–30% of my instructions to be loads, right? Why on earth would I scale everything uniformly, right? Similarly, some things are more expensive than others. Why on earth would I build 4 multipliers? Why on earth would I build 4 dividers that don't even show up on the chart? That would be very silly, right? Okay, but in terms of all the resources needed, load is our poster child for resource usage. Stores a little less, branch a little less. Jump is very simple, right? Jump is just a PC update. Okay, now, while this happens to sort of naturally correspond to the 5-stage pipeline that we're going to sort of see as the logical way to implement MIPS, there's nothing magical about 5 stages, right? And in particular, there's some causality reversal going on here as well. Remember, pipelining is older than MIPS, and MIPS was designed to be pipelined, right? People did not magically discover that this was a good way to do things and it happened to pipeline well. It's entirely the other way around. This was built from the ground up for pipelining. Pipelining is really, really old, right? So again, the great truism of computer architecture, IBM did it first in the 1960s, in the library with the candelabra. No, we're not playing Clue. No, but IBM did it first in the 1960s. But the way exactly that they did it and the constraints they were under don't always necessarily translate directly to the microprocessor space. And so, for instance, when we look at the difference between Tomasulo's algorithm, 1967, and when we first had dynamic scheduling in microprocessors, they were worried about some different things. They had different people they had to satisfy, and so they end up looking a little bit different. Okay, right, so pipelining, good, right? Pipelining is one of those optimizations that just almost always makes everything better. It is very low marginal cost to go from this design here to a pipeline design, right? There's complexity of thinking, but you solve that at design time. The dynamic constraints that you're running into are not too hard to resolve dynamically, right? This is a whole lot of bang for your buck. So the best assumption is that anyone who has 3 transistors they can rub together as their budget is going to pipeline it, right? Okay, now under ideal conditions, with a large number of instructions, neither of which are, and remember, ideal never happens. You're going to try to approach the Flynn limit. So basically, as your CPI approaches 1, your speed up approaches the number of pipeline stages. Right. So to the degree, and again, this is truer for smaller numbers, right? So going from 1 cycle to 5 cycles probably is going to actually be reasonably close to a 5x speedup, because I am going to be able to make my clock much faster. And to the degree that I couldn't, that this is uneven, right? I can go deeper than 5, right? I can split this into hundreds, right? And then I get a 1, 2, 3, 4, 5, 6, 7, 8-stage pipeline. Right? I'm going to find sort of the right balance from the sort of the hardware complexity of chopping it up. And if I chop it up into 8 stages, am I going to get actually an 8x improvement in my clock? Probably not. But I'm probably going to get like 7. It's going to be pretty good, right? Now, where this becomes more complicated as this number of pipeline stages keeps getting larger and larger is pipelines work perfectly. Your ideal case is when everything is feed forward, right? If I have a purely feed forward network, right? No dependencies across the pipeline. Like if I'm literally just like pipelining natural gas or anything else, right? I might have some hazards in routing for merging these together, but basically everything goes one direction and everything just flows. You're going to get very close to that ideal speed up. In pipelines of instructions have dependencies, right? My instructions are not all completely independent, and so your pipeline is not all feed forward, right? So everywhere in your pipeline there is a loop. There is the potential that you will not achieve the full performance boost of your pipeline. Right? So all of your data stalls, again, for more complex designs, all of your structural or control hazards certainly, right, are going to show up. And this is going to still be true when we go superscalar. Right? So your superscalar designs are also going to be pipelined. They're going to have more interesting cases. You're still going to have to worry about any of the loops that show up. That's going to be the ultimate limiter here. So we'll spend most of our time, at least during review, until we hit the superscalar. And even when we hit superscalar, we'll mostly stick to this this model here as our go-to proxy for a prototypical pipeline design. Again, nothing magical about 5. Lots of other depths exist. You need to fetch the instruction, figure out what it was, do it, which is in this case split between exec and memory. Right? You can certainly imagine a design where there's just do it, right? Where you don't differentiate between whether it's arithmetic or memory, and then make sure that the state is updated. Again, similarly, depending on the relative costs of these as you scale it, some of these things could be merged together, right? And these are all the steps. Get the instruction, figure out what it actually does, get the operands if they're local, if any execute on any local operands, get or set remote operands or results, and then update local state so you can do it all again. Okay. Ideally, wanders on through, life is happy. Nice and clean. Okay. So again, as you go deeper and deeper, right? Remember what the pushback on this is going to be. So if I go from a 7-stage, or let's go with the 8-stage model where I chopped everything into 100 nanosecond chunks. If I go from an 8-stage to a 16, chop them all in half again. Again, remembering that the setup and hold time constraints on registers are independent of your pipeline depth. So there are some constant costs baked into your cycle time. The faster and faster you run that clock, the larger and larger a fraction of your overall clock cycle is spent doing, basically the administrivia of the cycle, remembering, what you started with, getting that data, sending it to the compute units in that cycle, and then remembering it for the next stage. So if you took that to its extreme, you could imagine something where basically no work is actually happening because you're spending your entire cycle on just getting the data out of the register and putting it into another register. And in fact, if the two things that need to do the work are sufficiently far apart on chip, you actually do this. The Pentium 4 had entire pipeline stages where the only thing that happened was it went out of one register onto a bus, not a particular wire. So basically had to arbitrate onto the bus and then got stored somewhere else on the chip, right? So at scale, again, that's when they were trying to go very deep, right? So then they're going, you know, up to like a 50-stage pipeline for the deepest that they went with the very end of net burst. Yeah, you can get some diminishing returns. Let's just leave it at that, right? Okay, we got 5 minutes left, so let's try some Kahooting. Let's see if this works. Let me